Do 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 do. In this video, we're going to continue talking about momentum, and we're going to expand on it a little bit by looking at something called the momentum impulse theorem. So, what the momentum impulse theorem is, well, actually, let's get to it by first taking a step back and looking at Newton's second law. So, Newton's second, when we talk about it in terms of momentum, was the change, or the net force, was equal to the change in momentum divided by the change in time. So if I actually rewrite this, I can multiply both sides by the change in time. Where do we fit it here? So this will cross out here. So what we get is the net force times time gives us the change in momentum. And this is a useful thing to write because it leads us to something called impulse. Impulse is defined as force acting over time. And if you take a look at that definition, force acting over time, and look at Newton's second law here, what do we have? Force times time, or force acting over time. So force is actually or impulse, I should say, is just equal to this. The symbol we use for impulse is J, uppercase J, so this is impulse. And we said it's force acting over time, which is the change in, or the net force times time, which is also equal to the change in momentum. So this is actually what's called the momentum impulse theorem. Let's actually put a box around it. And we're going to call this the momentum impulse. Impulse, there we go, theorem. So it's relating the change in momentum to be equal to impulse, this new thing called impulse. And it's also equal to the net force times time. Let's take a look at the units of impulse here. So the units of impulse should be the same as the change in momentum. And change in momentum is final momentum minus initial momentum. All momentum has a unit of kilogram meters per second. So guess what the unit for impulse will be as well? The unit of impulse can be kilogram meters per second. However, even though this is correct, we usually use a different unit for impulse, which relates back to what we're actually talking about. It's force acting over time. Well, force is Newton and time is seconds. So when we talk about the unit for impulse, we actually usually refer to this as Newton seconds. And these two are actually equivalent. If you remember, a Newton is a kilogram meter per second squared. So if we take kilogram meter per second squared and then multiply by seconds, we have seconds in the numerator and in the denominator here. That will simplify to kilogram meter per second, which is the same thing as the unit we use for momentum. However, when we talk about impulse, usually we talk about Newton seconds. Let's look at an example of where we would use this momentum impulse theorem. So we have a tennis ball with a mass of 150 grams is hit and accelerates to 140 kilometers per hour in a time of 0.35 seconds. So this would be a serve, I guess. What was the average net force applied to the ball, and what is the impulse applied to the ball? So let's write down what we know here. We are given a mass of 150 grams. We always want to turn it to kilograms, so we'll divide by 1,000. That gives us 0.150 kilograms. We have VI is 0. We have an accelerates to 140 kilometers per hour, so that would be our VF. 140 kilometers per hour. Who likes kilometers per hour when we're doing questions like this? We need to convert that to meters per second. So let's divide by 3.6. That'll give us 38.9 meters per second in a time of 0.35 seconds. So we have time is 0.35 seconds. Okay, what was the average net force applied to the ball? So take a look at the momentum impulse theorem. We have impulse equals the net force over time is equal to the change in momentum. So if we're looking for average net force, we're looking for this part. Let's deal with the right half of this. So we'll have net force times time equals change in momentum. Net force, we'll divide both sides by the change in time. This is actually just going back to Newton's second. So our change in momentum is mass times Vf minus mass times Vi divided by the change in time here. So the mass stays the same, so really I could have written this as m times Vf minus Vi divided by change in time. And sometimes I'll even write that here, that this is the same thing as m times Vf minus Vi. So let's go ahead and plug some stuff in here. So we have 0.150 times 38.9 subtract 0 divided by 0.35. And when we solve that out, we get 16.7 newtons. So that is our average net force right here, 16.7 newtons. The second part to the question is, what is the impulse applied to the ball? So impulse, if we take a look at this, what do we know? Well, we now know that impulse is equal to the change in momentum. So I can just write impulse is equal to the change in momentum. We know that the change in momentum is m times Vf minus Vi. If the mass changed, you would have to do mf times Vf minus mi times Vi. But in this case, the mass of the tennis ball stays the same throughout, so we can just use m here. So we know the mass is 0.150. Final velocity was 38.9, subtract initial velocity of 0. And if you take a look, this is actually the numerator from over here, which makes sense. And this gives us 5.84. And normally when we're talking about impulse, we would say Newton seconds, or you could say 5.84 kilogram meters per second. Either way, I like the first one. That's the way you're going to see impulse written with these units, but both work. Let's do one more example. So again, dealing with a tennis ball comes towards you at 140 kilometers per hour, and you hit it back at a speed of 100 kilometers per hour after the racket is in contact with the ball for 0.35 seconds. What impulse and average force did you apply? So if we draw ourselves a little picture here, here's my racket. Sure it is. Yeah, why not? That looks like a racket, right? And we've got our tennis ball over here. Sure. Yep, that's totally a tennis ball. So it's coming in this direction at 140 kilometers per hour, and that would be our VI. And then we're returning it in this direction at 100 kilometers per hour, which is our VF. We have to actually be careful. These are in opposite directions, so we need to decide which one's positive and which one's negative. Let's say coming in is negative and this way is positive. In both cases, we should convert to meters per second, so divide by 3.6. This will give me negative 38.9 meters per second, and this one will give me positive 27.8 meters per second. We do have to pay attention to these positives and negatives. What else do we know? We know time is 0.35 seconds. And that's it. That's all we're given. So we're asked for what impulse and average force. So, I guess we have our mass of our tennis ball from the last question, which was what, 0.150 kilograms. That is kind of important, actually. So we're looking to find what impulse and average force. So let's use the impulse momentum theorem. So impulse is equal to net force over time, or the change in momentum. If I want to know impulse, we can solve that right away, or by plugging stuff in, or let's do net force first. So net force is going to be the change in momentum divided by the change in time. So that will be equal to m times Vf minus Vi divided by change in time. The mass was 0.150. Now is when it's important that we keep track of our positives and our negatives. Our Vf was positive 27.8. Subtract our Vi, which was negative 38.9. So double negative, this is adding here. All divided by 0.35 seconds. So please be careful. Let's maybe even me be a little bit more careful with my notation here. Put square brackets around the big thing and circle brackets around here. So when we solve that out, when you simplify that, on the top you get 10.0, positive 10.0, divided by 0.35, which gives me a net force of 28.6 newtons. The other part of the question said, what was the impulse? So we're looking for impulse. Impulse is just the change in momentum, which is the numerator from this part over here. So since we calculated it, we already know it's positive 10.0. Not newtons, though. This would be Newton seconds. So positive 10.0 Newton seconds. And just to be clear, this is where we got that positive 10. The numerator is the change in momentum. So using this formula, using different parts of it, and also knowing that the change in momentum is mass times Vf minus Vi, and of course everything here should be vectors. So using different parts of this momentum impulse theorem, you should be able to go ahead and solve questions number 1 through 5 on that momentum and impulse worksheet.